Is called Heart Disease 101, and we're going to do our best to provide a straightforward overview of heart disease from the engineering perspective. First, why are we software engineers here to talk about heart disease? We are in the somewhat unique position of having absolutely nothing to lose by calling a spade in this field. And boy, are there a lot of spades. After a lot of research, I feel confident making the assertion that most, if not all, of the information you have received to date on heart disease is hand-wavy fluff with little practical application in terms of either preventing or reversing the disease. The landscape in heart disease research is full of essentially useless epidemiology and lacking in rigor and actionable discoveries. The mainstream hypothesis cannot explain most of the observations, and the most experienced individuals in the field don't even accept the mainstream hypothesis. Just to recap, the diet heart hypothesis says two things. First, fat in the diet, and particularly saturated fat, raises cholesterol, particularly LDL or bad cholesterol. And second, cholesterol in the blood, and particularly LDL, drive heart disease. This whole saga is, without exaggeration, a disaster. Lacking good research in this area, our nutrition and public health recommendations have been led by fear-mongering based on paper-thin science. In case you don't believe me, here is Konstantin Velikin, a renowned pathologist with decades of experience and more than 300 published peer-reviewed papers on heart disease. No single etiologic agent and pathogenetic mechanism have been clearly implicated as yet in the onset of early lesions in human coronary arteries. Also, no useful result was reached during an entire century by continuing to put forward one theory to the exclusion of others. This is from Velikin's book, The Natural History of Coronary Atherosclerosis, which is, as far as I can discern, the single most comprehensive and accurate book ever written on the topic. I will be quoting it frequently during this talk. From my perspective, this book is required reading on atherosclerosis. It is unfortunately out of print, and good luck getting a copy. Don't tell anyone, but I have made a scan for personal archival use. Or we can ask Michael I. Gurr. He literally wrote the textbook Lipids and had the following thoughts on the diet heart hypothesis. The reviewer holds the view that the roles of diet and of dietary lipids in particular have been overemphasized, that the relationships between dietary lipids and coronary heart disease have been oversimplified, and that as a result, much of public policy is at best inefficient and at worst misguided. FYI, they always seem to use understatement when making these statements in scientific literature. Whenever I see this, I think of the Key and Peele skit with Obama's anger translator.
Because despite our differences, we count on the press to shed light on the most important issues of the day.
And we can count on Fox News to terrify old white people with some nonsense.
I will not be giving the Obama courtesy throughout this talk. We simply need to do better. This topic is of paramount importance to every human alive today, because not only can understanding heart disease inform our nutritional decisions, but also heart disease remains one of the largest causes of premature death. So let's dig into heart disease. My first introduction to this happened about a month into eating a ketogenic diet. I was seeing incredible improvement eating a high-fat diet. I think at the time, a typical breakfast involved about half a brick of cream cheese, inside an omelet fried in 4 tablespoons of butter alongside a latte made from heavy cream. Ted Naiman, please look away. But at some point, one of my friends reminded me that fat was bad, and in particular, that saturated fat causes heart disease. And as I thought back, I remembered that the only substantial thing I learned throughout my nutritional education was that fats and oils were bad and to be used sparingly. It was indoctrinated into me since elementary school. I actually went back into my backups and found hearthealthy.doc from March 3rd, 2003 from my 4th grade science class nutrition section. It says, try not to eat too many oils or too much butter. As you can see, 4th grade Nick was not the master linguist you see before you today. But this presents a clear dilemma. If indeed LDL is the devil and causes heart disease, why do I seem to be so healthy? If I asked a random doctor, they would consider me to be in excellent health despite eating a carnivorous diet. For this diet heart hypothesis to be correct, there has to be a strong discordance in key health outcomes. You can imagine this like a large balance. On one side, eating carnivore has improved, for me, BMI, fitness. I went from literally obese to abs. Insulin, HDL, triglycerides, I have excellent microbiome diversity, happiness, energy levels, no more Kiko eating disorder where I'm constantly afraid of food, simplicity, sinus headaches are gone. You get the point. Pretty much everything besides LDL. And on the other hand, my LDL goes up. And at the end of the day, this is an optimization problem. And either everything on the left ends up being more important, or the one thing on the right ends up being important. And we need to figure that out by ascertaining the importance of LDL. How does the mainstream medicine explain all this heart disease business? Beyond the diet heart hypothesis, mainstream medicine uses the pluricausality hypothesis. This is the following. There was a scientist named Anichkow in 1913, and they had tried for a while super duper hard, and they just couldn't figure out what was causing heart disease. And he said, well, I can't find the one thing that's causing heart disease. Maybe everything is causing heart disease together-ish somehow. And that, ladies and gentlemen, is the model used by the mainstream medical and research community to explain heart disease. There's just one problem. It's a logical fallacy. I will show you what I mean. Human plaques tend to be morphologically similar in all populations studied. Adults with increased serum cholesterol levels show the same type of fibrofatty plaques as those who are normal cholesterolemic. Although diabetes enhances the rate of development of clinical atherosclerosis, plaques from diabetics have the same morphology as do those from non-diabetics. Therefore, a variety of risk factors result in the same type of pathologic lesion in the vessel wall. Basically, all this is saying is these risk factors, high cholesterol and diabetes, do not alter the heart disease in any way. Right? Can anyone spot the error? Hint, risk factor means associated variable. They've confused correlation with cause, right? Any reasonable human, given the observation that heart disease is identical, whether or not you have elevated cholesterol, would conclude that cholesterol is not the cause of the disease, right? There's another explanation available, namely that each of the risk factors they've discussed are merely risk factors, associated variables, and are not substantially involved with the actual cause of the disease. It is totally plausible that a yet-to-be-identified cause drives atherosclerosis and elevated cholesterol. These people are hoping that if they use the word risk factor enough, it will start to mean mini-cause instead of associated variable. I'm not joking. I think a lot of people in public health have forgotten the definition of risk factor. Konstantin Velikin said quite plainly that he considers the multifactorial model based upon the available risk factors to be insufficient. And I haven't even told you where I got this quote. It's lifted directly from the cardiovascular pathology textbook. Is that bad? Yes. A valid question then, why has the multifactorial model remained so popular despite it being stupid? In the real world, when you see a weak association, for example, bacon is associated with 13% more cancer, we cannot assume there is cause here. We assume that these are tangentially associated via several degrees of separation. In this case, it's probably a weak proxy for affluence or healthy user bias. In heart disease fun time land, they don't like that. They have a lot of weak associations, and they don't want to live in reality where weak association precludes cause. But if we assume, without any evidence, that somehow many different things cause the disease magically together somehow, we can then suddenly argue that weak association is cause. Does anyone know what this is called? There's a technical term for it. Bullshit. This framework is at best implausible and never itself validated. It is from this glorious belief that we get statements like, doing X will lead to risk. What are they talking about? That's nonsense. I would absolutely love for some pathologist somewhere to show me what a risk looks like under a microscope. Same with modifiable risk factor, modifiable associated variable. Again, nonsense. It's a manifestation of the fact that our public health community is basically this. This should read, in a study with this population and these adjustments, X was associated weakly with disease Y, right? There's no leading going on in association. Unfazed by these shenanigans, Nathan and I are looking for the cause of heart disease. Where to start, though? Google looks like a good bet. I actually did Google, does saturated fat cause heart disease back in 2014, and I got to a page on Wikipedia detailing the controversy over whether or not saturated fat causes heart disease. And this page displayed a table with reputable journal studies, and a couple said yes, and the other half said no. This table's a bit of a train wreck because several of the positive analyses have caveats like, well, nobody actually lived any longer, or the bottom one which warns that you might get harm if you substitute carbohydrates for saturated fat, i.e. that like butter is better than bread. But there's some good news. Thankfully, some genius actually fixed this by going back and throwing an appeal to authority logical fallacy into the page's introductory paragraph. I think a salient indicator of shenanigans is when they don't even lead with there is good evidence for this. They just say a bunch of handsomely pharma-funded organizations agree with one another. To clarify, colloquially, or in common parlance, we consider heart disease to be roughly synonymous with atherosclerosis. And to clarify the current state of the art on understanding atherosclerosis, I'll let the National Institute of Health clue us in. We go to their webpage on atherosclerosis, scroll down to the cause section, and you find this absolute gem of a sentence: the exact cause of atherosclerosis is not known. First, this is mortifying, especially so to anyone who ever avoided bacon in the name of preventing heart disease. But second, I'm very concerned because a lot of people claim to know what causes heart disease. That means, by the transitive property, that a lot of people are probably lying to us, right? So we require caution in interpreting research and guidelines in this field. And before we go much further, we need to define the word atherosclerosis itself. What is the definition of atherosclerosis or heart disease? Does anyone know? That's actually a trick question. There isn't one. I know that must sound absolutely hilariously ridiculous to you, but it's actually true. The research at large is exceedingly laissez-faire in what they define as heart disease. Each researcher sort of picks whatever definition suits them at the time. To illustrate this, Konstantin Velikin compiled 59 examples of different investigators choosing their own definitions. A few key takeaways and examples. Many definitions stress proliferation, which means growth. Atherosclerosis is fundamentally a proliferative disease in its early stages, and atherosclerosis does not happen without abnormal growth. It is reasonable to regard atherosclerosis as a proliferative response to vascular injury, and all later changes, such as accumulation of lipid, fibrin, etc., as a secondary event. Gresham, 1983. Development of a lesion requires that smooth muscle cells migrate from the media into the intima and grow in the quite different environment of the intima. Schwartz and Highmark, 1985. So this says requires, not usually happens, right? How many of you have never heard before that atherosclerosis is a proliferative disease? Why have you never heard that basic fact about this disease? Why is it that this well-known fact appears nowhere on the National Institute of Health website on atherosclerosis? How many doctors in the room are willing to admit that they had no idea that atherosclerosis was a fundamentally proliferative disease? I'm just kidding. I'm sure you all knew already. Many definitions emphasize the failure of the diet-heart hypothesis. The definition of lipids is not the activator, but only the indicator of pathological connective tissue changes which take place in the vessel wall. Garrow and Bahari Varga, 1976. The term atherosclerosis has unduly stressed the role of lipids, resulting in an inappropriate conceptual emphasis. Lipid is often not a major feature of the disease, and the disease frequently exists without lipid deposition at all. Rank, 1985. This one says, any theory that attempts to explain atherosclerosis must address this whole spectrum of changes, not just one of its components. Constantinides, 1979. That, for the uninformed, is how a scientist does a shots fired at the LDL hypothesis. And there are many references to immunological effects and repair. Atherosclerosis may be triggered and or accelerated by the abnormal response of some areas of the vessel wall to the cumulative and often synergistic effects of recurrent injury repair cycles, resulting in permanent arterial damage. Robertson, 1977. And out of fairness, one doofus. Atherosclerosis can be defined as a disease process that occurs when the influx and deposition of cholesterol into the arterial wall exceed the egress of cholesterol from the arterial wall. Mahley, 1983. This is Kiko 2.0, cholesterol in, cholesterol out. Besides being, just wrong, this is about as enlightening as Kiko 1.0 was on weight management. There's also quite a bit of heterogeneity. My favorite science burn came from Velikan here, who said, there is also no evidence that the value of innumerable meetings in atherosclerosis was in any way diminished by the absence of an adequate definition of the disease on which the discussions were focused. Loved that one. Gave me a little chuckle on the plane when I read that. Even the word itself is interesting. Atherosclerosis comes from Greek roots athero, meaning porridge, and sclerosis, meaning fibrous. So the word itself means fibrous porridge, which is a vague aesthetic description of this, what arteries with fibrofatty lesions look like. Quoting cardiovascular pathology textbook again, the term atherosclerotic plaque is still much used, but conveys little information about the nature of a plaque. So our goal is to develop a hypothesis that explains atherosclerosis. To start, in disease research, we do pathology, the study of disease and particularly deceased tissue. Basically, by doing tons of autopsies, we can start to get an understanding of what the disease looks like, where the disease is, what's inside it, what it looks like under a microscope, how it differs in people with differing ages and lifestyle factors. At the arterial level, the disease is characterized by a series of changes to the artery wall. We call these lesions. From Wikipedia, it's basically the Latin word for injury. So starting at square one, the heart is a blood pump. And in order to do that work, the heart itself needs blood, so this coronary artery loops back around to give the heart nourishment. When someone gets a heart attack, it is due to problems with this system. The traditional theory is called the hydraulic hypothesis, which is basically a tube getting clogged. I hired a world-renowned illustrator to put this together, so get ready. First, atherosclerosis causes the artery to narrow. Second, something triggers a clot or a scab to form inside the artery. Usually the plaque ruptures, like it pops. The narrowing gets plugged with that clot, and then the heart gets insufficient blood flow and starts to be unhappy. The public messaging via phrases like fat clogs your arteries will most likely have given you the impression that atherosclerosis functions as a bacon grease in the cold drain pipe model, where fat gloms onto the side of arteries. That is 100% false. As we can recall, when heart disease begins, the first abnormality we see is actually abnormal growth, not abnormal accumulation or degeneration. The exact problem is abnormal dedifferentiation and proliferation of vascular smooth muscle cells, specifically that they switch from the contractile to the synthetic phenotype. So I'm going to translate that for you. This is an artery. It has several layers. Some arteries, like the coronary artery, have muscle cells in them, which help the heart pump blood around the body. It's kind of cool. The muscle cells are in this layer here in the middle called the media. Something weird happens, and these cells stop behaving like muscles. Muscle cells in the muscly mode are called contractile phenotype. They have a repair mode called the synthetic phenotype, think synthesis, and they switch to that. They start to grow or proliferate and actually cross the boundary into the intima. This is abnormal. The first problems seem to result when the arterial intima reaches a critical thickness which is beyond the normal range and beyond which oxygen can easily diffuse. One note, normal muscle cells in the contractile phenotype, i.e. behaving as muscles, don't accumulate lipid or cholesterol. After they dedifferentiate, lipid and cholesterol accumulate in the tissue. The dedifferentiation causes a change in lipid metabolism in the cells. This is basically step one of heart disease. It's required, again, no proliferation, no disease. Right? We have different types of lesions. There will be a quiz after the lecture, but you can see the list here, and conveniently there's actually no standard classification scheme. The more you dig into this, the more of a dumpster fire it gets, but I'll go over some interesting notes here. There are two early lesions, gelatinous and fibrous. Gelatinous lesions contain little or no lipid and have not been extensively studied and are not referred to in many of the current theories of atherogenesis. If you think I'm kidding, again, this is a direct quote from Cardiovascular Pathology, 3rd edition, page 73. I've actually had someone try to call my bluff here because that can't be correct, as there's no way in hell that anyone would make recommendations to lower cholesterol based upon our understanding of this disease if that were the case. Also, fibrous lesions. These are early lesions that have a fibrous appearance to them due to fibrin, the clotting protein. They also often lack cholesterol and lipid accumulation and can exhibit tiny little scabs. Here's why this is interesting. If I wanted to argue for the response to retention hypothesis, i.e. that retention of LDL is what causes the disease, the first thing I do is get a graph of time versus tissue lipoprotein concentration, right? Because temporality is important for cause. So you'd have time starting at healthy and advancing to an advanced lesion, and then you'd plot whatever function that was on how much lipoprotein is in the tissue at each time. Where is that graph? I'll give you a hint. It doesn't exist. Why doesn't it exist? Because it doesn't support the axiom that LDL is the cause. In fact, if you ask a very simple question like, what's the normal concentration of LDL in the healthy artery wall? There are only 2 papers ever published that I've found answering that question, providing 2 irreconcilably different answers. Nobody even seems to care enough to establish basic knowledge that is a prerequisite for critically evaluating a hypothesis like response to retention, right? In my humble opinion, that's pretty damning when it comes to quality of science and argument. So what we'd expect if retention of LDL was the cause of heart disease is temporality. First, LDL shows up and increases the concentration above healthy. Then disease happens, right? So E.B. Smith in 1977 measured intimal LDL concentration at double serum. First, that's interesting because it means that the healthy artery actually grabs and pumps LDL into itself for some reason. Per Velikan, some gelatinous lesions may have less LDL than serum. So if that's the case, the graph actually looks like this, right? How is response to retention a valid model if the first step in atherogenesis is a reduction in LDL concentration? Temporality hasn't been established, right? So continuing on, fibrofatty lesions. These are the namesake atherosclerotic lesion containing a lipid core surrounded by a fibrous cap which stabilizes the plaque. It is possible to create one of these in a rabbit by attacking their aorta with a catheter, like via physical damage, creating what's called a mural thrombus. Interestingly, a fibrofatty lesion exhibits accumulation of free cholesterol, measured in one paper as a 6-fold increase relative to healthy tissue. Free cholesterol is not bound or esterified inside a lipoprotein like LDL, which means that it actually didn't come from LDL, because there's no way to de-esterify it, and it appears to come from cell membranes of red blood cells, which have somehow ended up in the middle of the artery wall. Talk to Malcolm Kendrick on that one. Saving the best for last, fatty streak. These are an accumulation of lipid near the surface of the artery. They are not technically a lesion because they don't appear to be pathological. They are essentially ubiquitous. Every child has tons of these streaks in their aorta by the age of 2. Even children that died in the post-war famine had them. But they don't appear to be a precursor of any of the other lesion types, and most will spontaneously regress, i.e. just vanish as we grow. Therefore, these are not disease. These are a normal anatomical variation, or at a minimum, a separate and independent pathology, so it's just distinct from an atherosclerotic lesion. Dock, 1974, proposed the term xanthosclerosis to indicate it being a different disease which bears similarities to sebaceous cysts. He says, "It is high time pathologists, editors, and medical index rejected the errors of the 18th century." Unfortunately, many doctors and lipidologists don't seem to be familiar with and or ignore the research indicating that these streaks are not the beginning of heart disease. Some examples. At some point, you likely heard a doctor claim that atherosclerosis begins in childhood based upon these streaks. Not to name any names, but Peter Attia. As you may infer, that's not correct. The first fibrous lesions aren't identified until later, 20s, except in heavy smokers when they may show up in the teens. Interestingly, the initial fatty streaks actually form in the aorta, so they're in kind of the wrong place. Fatty streaks don't seem to form in the coronary artery until about 10 years of age. So this is also a key area of discordance that I want to highlight. So people who advocate for the LDL hypothesis, I will call them LDL fans because there's a lot of hoorah going on, but they'll tell you that the LDL concentration in serum drives atherosclerosis. And they'll advocate for lowering of LDL to prevent atherosclerosis. I've heard some say, for example, that with an LDL of 30, we would have no heart disease. They will also try to define fatty streaks as atherosclerosis despite the contrary evidence, primarily because if they don't, the hypothesis is kind of dead in the water because the other early lesions like fibrous and gelatinous often lack lipid. Remember the graph I showed to you? But babies actually have exceptionally low LDL, yet they develop tons of fatty streaks. So we've shown that low LDL doesn't preclude the development of fatty streaks. LDL fans have also been known to cite babies' low LDL as justification for using drug and dietary interventions to lower LDL, even though they're getting fatty streaks while they have low LDL. And then most of the fatty streaks spontaneously regress as the LDL in your blood goes up with age, right? If you're confused, you probably should be. This really doesn't make any sense at all. And on LDL, I also just wanted to point out Simpson's paradox. So this is where a trend exists within a group of data that disappears or changes when combined in a larger set. As the background, there's this one golden study by Stamler that every vegan whips out to show you that total cholesterol is a killer. And I want to make it clear statistically how we can explain some of this discordance. So if we simplified the lipoprotein system, we could say we had three states. One of them is normal, with an LDL of something like 100, reasonable triglycerides and reasonable HDL. Then we could have dyslipidemia, which is the classic problem of elevated LDL, low HDL, and elevated triglycerides. And then we could also have a low-carb LMHR, which had elevated LDL along with optimal HDL and triglycerides, right? So if in this case, let's say dyslipidemia was associated with a 2x increase in risk of death, and lean mass hyperresponder was associated with a 95% reduction in risk of death, right? Two totally opposite directions. By looking only at column number 3 here, the sheer number of unhealthy people in row 2 with dyslipidemia are going to overwhelm this statistic and make it look like there's a net problem with having elevated LDL if you don't break it apart and differentiate by the other metrics. This is the whole question behind Dave Feldman's low-carb cholesterol challenge. If you control for these other variables, it allows you to see a level deeper and see the underlying trends, right? The major game here is that the body is trying to fix the problem. Many of these processes seem to act to heal and stabilize the plaque. These include things like calcification, so that the body forms a bone matrix-like structure in the arteries. And also fibrous caps seem to be critical to stabilizing these larger plaques and preventing them from rupturing. Here's a key point. So a stable plaque doesn't seem to cause problems, even if it blocks most or all of the artery. Heart attacks seem to be driven by a very acute event like that, like a rupturing unstable plaque. And it seems that the degree of narrowing isn't that important to how deadly a plaque can be, which is one of the difficulties surrounding the use of imaging to try and identify where to apply treatment, like a stent based upon narrowing. What this means, and this is key, is that atherosclerosis per se may not be the most important aspect of a heart attack or other cardiac mortality. If that's the case, a high amount of atherosclerosis may not be a huge problem if you've made a lifestyle change to address the root cause of the disease and the body is able to stabilize the plaque. Under the hood, the heart has tons of what are called collaterals, so you can actually have a totally occluded coronary artery that is effectively bypassed by other vessels and have no heart damage at all. Its clear stabilization, therefore, is very important. If the fibrous cap is weakened, this can rupture, triggering a blood clot, which can lead to one of two bad things, either the growth of the lesion when the clot is reincorporated into the wall, or a heart attack, at least that's the theory. It would appear a major driver of such destabilization, or fibrinolysis, is acute immune activation. In the microscope slide, you can see the large number of macrophages in the thin fibrous cap. We get a substantial increase in heart attacks in the 7 days following a respiratory infection. It's literally a hazard ratio of 48. So I'm going to distill this into key takeaways. TLDR, nothing about the pathology of this disease supports a hypothesis that serum concentration of lipoproteins like LDL are a driver of disease. Rather, it suggests they are a bystander. The temporality, pathology, timeline, and structure do not align with a response to retention model. 2, the disease is highly localized. It tends to happen in particular places, apparently determined by the blood interaction with the wall of the artery. The most plausible hypothesis to explain this business basically boils down to three things. One, immune activation of some sort is driving this disease. Two, the immune system is reacting to something in the blood that shouldn't be there. And three, the immune activation is not completing, per se. An immune response starts by destroying the problem, but we should finish by repairing the damage, and we don't seem to get that far. One hypothesis to explain this is that the immune system is constantly activated in kind of a localized manner in specific places, and is thus prevented from finishing the immune cycle. Risk factors do get us something valuable. We are correct in the observation that many diseases are associated with heart disease. One easy way to explain this would be if something was in common with all the different conditions. So what do all these diseases have in common? Well, there are only so many options to investigate. As we start to dig further into this, one point comes up again and again. All of these diseases have immunological associations. There's this book called The Inflammatory and Infectious Basis for Atherosclerosis, which is, to be honest, really terrible, but many of the articles mention this one interesting tidbit. Something called endotoxins seem to trigger immune response. And so the first question is, what are endotoxins and how the hell did they get in the blood? Endotoxins are little bits of bacteria. For time immemorial, multicellular organisms, of which we are presumably a subset, have been at war with these little bacteria. Basically, we are large, warm bags of nutrients, and bacteria kind of like to move on in and hang out. Some of this is good. A symbiotic relationship between gut bacteria and a cow are what enables the cow to ferment cellulose and turn that gross, unappetizing lettuce into delicious steak. But the body sets up a bit of a firewall. We are fine having bacteria in the digestive tract, but if they get into the blood, the body kind of goes into a panic mode and tries to murder all of them. This makes sense because bacterial infections can kill us. This process of keying off little bits of bacteria is called the innate immune system. It doesn't need to be trained to recognize these things. Our body has special receptors called toll-like receptors, which are just sitting there waiting for a little bacteria so that they can raise an alarm. Dave Feldman came up with a great analogy for this. The innate immune system is analogous to like a building fire alarm and fire suppression system. Fire is a common enough problem that we build all our buildings with these protections built in. When you take a step back and look at the innate immune system, many puzzle pieces start to fall into place. So for example, endothelial cells on the inner surface of the artery wall express these innate immune receptors like TLR4 and TLR2. And this makes sense. They are the first cells which are going to be in contact with pathogens in the blood. If there were endotoxins in the blood, they would trigger an immune response when the blood interacted with the artery wall. But you say, Nick and Nathan, an infection is an acute event that will get dealt with. How does it cause a long disease like atherosclerosis? Here's the rub. Let's zoom into the digestive tract. Here we have kind of a big, happy family of tons and tons of bacteria having a grand old time. There are also tons and tons of dead bacteria and tons of endotoxins, with literally one cell width barrier between this fiesta and your bloodstream. Under ordinary conditions, your digestive tract will do something really cool. It absorbs exactly the things your body wants, all the nutrients, and leaves the things it doesn't, like endotoxins. How does it do this? Literally magic. Over the course of evolution, we shoved a bunch of food in there, and we evolved to handle it. Basically, any proto-humans that couldn't digest meat well were outcompeted by those who could. Now fast forward to the agricultural era and the past 100 years, and suddenly we are shoving this into the system. To put it mildly, the digestive tract has not evolved to handle a Twinkie. The exact ways in which the food interact with the digestive tract are incredibly complex, and I would classify our current understanding as basically zero. However, we can use the following model and approach it as a black box. If we put in the correct food, we expect a healthy digestive tract and low toxin absorption. If we put in the wrong food, we expect an unhealthy digestive tract and high toxin absorption. So from this, we can work backwards starting from the endotoxin response. If whatever we're doing results in a low endotoxin absorption, it's good. And if whatever we're doing results in a high endotoxin absorption, it's bad. This model seems to hold pretty well. Studies have shown that diabetics absorb lots more toxin than the average American without diabetes, which are probably moderately unhealthy. Nathan and I are working on experiments to compare endotoxin absorption between carnivores, normal individuals, and diabetics, under the assumption that carnivore seems like a diet completely devoid of food likely to cause intestinal problems. So, The hypothesis is atherosclerosis is an inflammatory disease driven by immune response to serum endotoxemia. Specifically, an incompatible diet results in serum endotoxemia. Serum endotoxemia triggers the immune response via the innate immune system, and the innate immune response results in chronic disease. One of the reasons I like this hypothesis is that it has two parts, and we can investigate them separately. So first, we figure out what aspects of diet and lifestyle drive endotoxin absorption. And then second, we figure out whether and how endotoxemia drives atherosclerosis. The latter point seems to be a bit easier. The more I research, the more data I find linking endotoxins to heart disease. You may recall that the first abnormality in heart disease is abnormal dedifferentiation and proliferation of vascular smooth muscle cells. The most likely reason that a cell would try to repair things is some sort of damage in immune response. A quick note on inflammation. People tend to have the vague notion that inflammation is basically something bad to be fixed with antioxidants from blueberries, right? That's wrong. Please do yourself a favor and dispense with that notion. To help conceptualize this, replace every time you see the word inflammation with healing. Inflammation is in charge of fixing problems and is used for various purposes within the body. Abnormally elevated inflammation is an indicator of abnormal damage, but is not a problem per se. Simply blocking inflammation will worsen the problem because now you slow the healing from the damage. This tends to confuse people, so I thought I'd clarify this. The key point here is we're able to explain the key observations about heart disease with this hypothesis. There's a lot, so I'm just going to breeze through these. First, the association with dyslipidemia. If you inject LPS into someone, they get dyslipidemia, i.e. dyslipidemia, elevated LDL along with low HDL and high triglyceride, may just be an indicator of endotoxemia. Second, association with hyperinsulinemia. If you inject LPS into someone, you get insulin resistance. This is apparently how the body ensures there's sufficient energy in the blood to fight infection. This doesn't necessarily preclude insulin playing a direct role in the pathogenesis, but lipoproteins actually clear endotoxins from the blood, so a mutation in the LDL receptor causes impaired clearance of toxin and elevated serum levels of LDL as a marker of reduced clearance. Note that we have mechanistically upstreamed the LDL fans that argue that LDL concentration is causal, and as such, Mendelian randomization and similar genetic shenanigans cannot differentiate between LDL and endotoxin hypothesis. And for smooth muscle cell proliferation, a low dose of LPS induces proliferation and the high doses have toxic effects. Intimal thickening, LPS results in thickened aortal intimas in rabbits after damage to the artery. MI after infection, LPS interferes with the blood flow of the coronaries and the coronary autoregulation via inducing vascular smooth muscle cell hypercontractility. I'll do a Heart Disease 201 talk on the fascinating dynamics of coronary blood supply and how interference with the complex systems of the coronary arteries might cause a heart attack. Blocking this pathway of innate immune receptors like TLR4 or deletion of a downstream signaling molecule like tumor necrosis factor reduces atherosclerosis in an ApoE deficient mouse model. Rheumatoid arthritis medicine reduces coronary events substantially. Rheumatoid arthritis is another inflammatory condition. And some other associations, organ rejection drugs designed to suppress immune response reduce rates of coronary events. Transplanted vascular organs experience dramatically accelerated atherosclerosis because the immune system reacts to the transplanted organ. The top medications, statins, CETP inhibitors, PCSK9 inhibitors, niacin, bile acid sequestrants, lower LDL and improve event rates, also have immune pleiotropy, meaning they also affect the immune system. Medications which lower LDL and fail to improve events have negative or null immune pleiotropy. And two examples of diseases that drive rapid heart disease are sickle cell anemia and Kawasaki's disease. Both have very strong immunological effects, which supports that the primary mechanism is immunological. Not only do such observations suggest that this pathway is central to heart disease, it also explains many more aspects of the disease than any other hypothesis, i.e. there are no paradoxes. We are thankfully not the first person to call out this hypothesis specifically, though there are not many people looking into it. So now the important part, how do you minimize your endotoxin absorption? If I had to go out on a limb, I would hypothesize that whole foods like plants and animals with evolutionary precedents, trigger less serum endotoxemia than processed garbage. Surprise, right? Eating a whole foods diet may stop chronic disease. I think that a lot of the improvement people see when switching to a keto or a carnivore diet may in fact be upstream of insulin resistance per se and more directly due to gut health and serum endotoxemia. Suffice it to say that more research will be needed here, though. So I also mentioned earlier that it would appear heart attacks are driven by acute events. We may find that the event rate or number of heart attacks in people on a whole foods diet without cheating or additional complications to be very low, even with advanced disease. I think that would be awesome. I want to provide a hypothesis. This is just spitballing, but that could potentially explain the way this would play out. So a normal person is going to have constant endotoxin pressure. The immune system isn't able to stabilize all the plaque. And then an acute infection or something else comes along and triggers a burst of endotoxin or immune response. And fibrinolysis causes the rupture and plaque growth or myocardial infarction. In comparison, a whole foods person who has eliminated endotoxin, even after 50 years of disease growth, the arteries can spend a bunch of time stabilizing and fixing the plaque. The same acute endotoxemia is not going to result in a problem since the plaque is stabilized, right? So that's kind of what we got so far. It's my hope that we can move towards a world where we increase familiarity with heart disease to the point that we can dispose of the imprecisions that have led us to the current abysmal state. The more we are able to correct and or ignore people who lack a strong understanding of the fundamental pathology of atherosclerosis, the more we stand to drive intelligent discourse and improve our overall understanding. Hopefully we can progress towards answers to these questions which have yet eluded us.